For centuries, we've looked up at the night sky, trying to understand the mysteries of the universe. With our eyes, we've seen the beauty of the stars. With our telescopes, we've unraveled some of its secrets. But what if I told you that everything we've learned so far is only part of the story? That beyond the light, there's something else, something more powerful, a way to hear the universe itself. What if we could feel the very fabric of space-time ripple and move? Hear the silent symphony of the universe's most cataclysmic events? This is not science fiction. This is gravitational waves, and it's rewriting everything we know about the cosmos. Gravitational wave is one of the most groundbreaking advancements in astrophysics and cosmology. It opens an entirely new window to observe the universe, revealing hidden secrets that couldn't be detected with traditional methods like light-based telescopes. By studying these ripples in space-time, we're unlocking cosmic phenomena that were previously impossible to study. But before we get into what we can hear today, let's first explore what these gravitational waves are. Gravitational waves are disturbances in the very fabric of space-time, caused by the acceleration of massive objects such as black holes and neutron stars. They travel at the speed of light, carrying with them the signature of the violent events that caused them. These waves stretch and compress space-time as they travel, but detecting them is no easy feat. They're extraordinarily faint. In 1915, Albert Einstein predicted the existence of gravitational waves in his theory of general relativity. He proposed that when massive objects accelerate, particularly during violent events like the merger of two black holes, they create ripples in space-time. These waves carry information about the event across the cosmos. But Einstein also thought they were so tiny, we'd never be able to detect them. Gravitational waves are transverse waves, meaning they distort space in a direction perpendicular to their motion. Imagine stretching and squeezing a rubber band as you pull it. It's a little like what happens to space-time as gravitational waves pass through it. But the stretching and compressing are so minuscule that only the most advanced technology can pick up their signal. The waves carry vast amounts of information about the events that generated them, such as the mass, speed, and distance of colliding black holes or merging neutron stars. With this new type of hearing, we can study phenomena that were once invisible. Detecting gravitational waves wasn't easy. Though Einstein predicted their existence in 1915, it took nearly a century for technology to catch up to the theory. In fact, it wasn't until 2015 that humanity finally caught its first direct glimpse of these cosmic ripples. Before we could directly detect gravitational waves, indirect evidence came from the 1970s, thanks to the work of Joseph Taylor and Russell Hulse. They discovered a binary pulsar system, two neutron stars orbiting each other, known as PSRB 1913+16. Over time, they observed that the star's orbit was gradually decaying, just as Einstein's theory predicted. The reason? These neutron stars were losing energy by emitting gravitational waves. This indirect evidence earned Taylor and Hulse the Nobel Prize in Physics in 1993, and it confirmed that gravitational waves were indeed real. But still, no one had actually heard a gravitational wave. In the 1980s, a new dream was born: the idea of building a detector capable of directly detecting gravitational waves. This dream materialized in the form of LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO uses a technique called interferometry. It's a bit like shining a flashlight down two tunnels, waiting to see if the light waves shift when something invisible, like a gravitational wave, passes through. At LIGO, two massive arms stretch for kilometers in an L shape. A laser beam is split and sent down both arms. When a gravitational wave passes through, it distorts the arms by an unbelievably tiny amount, thousands of times smaller than a proton. By measuring this distortion, LIGO can detect these faint ripples from distant cosmic events. After decades of development, LIGO was ready. And on September 14, 2015, the impossible happened. The first direct detection of gravitational waves came from a colossal event. Two black holes, each about 30 times the mass of the Sun, collided in a galaxy 1.3 billion light-years away. When they merged, they created a ripple in space-time that traveled across the universe. LIGO captured this ripple, named GW150914, and we finally heard the universe's gravitational hum. This event released an extraordinary amount of energy, momentarily more than all the stars in the observable universe combined. And it was proof that not only do gravitational waves exist, but we now had the means to detect them. Detecting gravitational waves is one of the greatest scientific challenges of our time because these waves are incredibly faint. The technology behind their detection has to be extraordinarily sensitive to pick up these minuscule distortions in spacetime. The principle behind LIGO and other detectors like Virgo and KAGRA is laser interferometry. Imagine two massive tunnels arranged in an L shape, each stretching out for kilometers. A laser beam is split and sent down both arms of the L. When gravitational waves pass through, they slightly stretch one arm while compressing the other. This creates a detectable shift in the laser beams when they recombine. These distortions are extraordinarily small, fractions of the width of a proton. That's why the instruments must be isolated from vibrations and external noise, like traffic or seismic activity. LIGO, Virgo, and KAGRA are constantly upgrading their systems, making them more sensitive and capable of detecting even fainter signals from deeper within the cosmos. After LIGO's first detection, the observatory continued to evolve. Advanced LIGO, which began in 2015, increased the sensitivity of the detectors by 10 times, allowing it to detect more frequent and distant events. But there's more on the horizon. Future observatories like the Einstein Telescope and the Space-Based Laser Interferometer Space Antenna, LISA, promise to detect even fainter gravitational waves from events even further back in time, including signals from the early universe. Gravitational waves come from some of the most energetic and extreme events in the universe. The first detection, GW150914, revealed the power of black hole mergers. But that's just the beginning. When two black holes orbit each other in a binary system, they lose energy through gravitational waves, gradually spiraling inward. When they finally collide, the resulting event is one of the most violent in the universe, releasing massive amounts of energy. These black hole mergers are now a common source of gravitational waves, providing new insights into the population of black holes in the universe. In 2017, LIGO and Virgo detected something even more exciting: the merger of two neutron stars. These dense remnants of massive stars are incredibly compact, and when they collide, they produce both gravitational waves and electromagnetic radiation light. This was the first time that astronomers detected gravitational waves and light from the same event, giving birth to multi-messenger astronomy. These neutron star mergers are also believed to be the factories where heavy elements like gold and platinum are created. This cosmic explosion, known as a kilonova, showed us where some of the universe's most precious elements come from. While black hole and neutron star mergers have been the primary sources of gravitational waves so far, they aren't the only ones. Supernovae, the explosive deaths of massive stars, are also expected to emit gravitational waves. However, detecting these signals is more challenging because they are fainter and more complex. There are even more exotic possibilities: rapidly spinning neutron stars, cosmic strings, hypothetical defects in spacetime from the early universe, and possibly the distant echoes of the Big Bang itself. One of the most exciting developments in gravitational wave is its integration with other forms of observation. This is called multi-messenger astronomy, where gravitational waves, light, and sometimes even neutrinos are detected from the same event. In 2017, gravitational wave reached a new milestone with the detection of GW170817, a binary neutron star merger. Just 2 seconds after LIGO and Virgo detected the gravitational waves, gamma rays were detected by space telescopes. This was the first time gravitational waves and light were observed from the same event, providing unparalleled insights into the physics of neutron stars and the production of heavy elements. Telescopes across the electromagnetic spectrum, from radio waves to X-rays, observed the aftermath of this event for days, giving astronomers a wealth of information about the merger and its explosive kilonova. As gravitational wave detectors become more sensitive, more multi-messenger events will be discovered. The combination of gravitational waves and light provides a more complete picture of cosmic events, helping scientists understand extreme phenomena like supernovae, neutron star collisions, and black hole formations. Beyond individual events, gravitational wave astronomy is poised to transform our understanding of the universe as a whole. By studying these waves, we can probe fundamental questions about the nature and evolution of the cosmos. Gravitational waves offer a new way to measure the expansion of the universe, known as the Hubble constant. When we detect the merger of two neutron stars, we can calculate the distance to the event from the gravitational wave signal. By comparing this distance to the redshift of the host galaxy, we can better measure the rate at which the universe is expanding, potentially resolving one of the greatest tensions in modern cosmology. Gravitational waves also allow us to explore the early universe. While electromagnetic radiation from the early universe is obscured by the cosmic microwave background, gravitational waves can travel almost undisturbed. Detecting these primordial gravitational waves could give us insight into events that occurred just after the Big Bang, such as cosmic inflation and the formation of the first structures in the universe. Gravitational wave is still in its infancy, but the future holds incredible promise. As detection methods improve, we'll be able to observe even more distant and exotic events, providing new insights into the fundamental workings of the universe. The future of gravitational wave includes new detectors like the Einstein telescope and the space-based LISA. These observatories will push the boundaries of what we can detect, opening up new windows into the most extreme events in the universe, including supermassive black hole mergers and potentially signals from the early universe. Gravitational wave has opened a new window into the universe, revealing cosmic events we could never observe before. From the merging of black holes to the collision of neutron stars, these gravitational waves carry the stories of the universe's most violent moments. We're now listening to the universe in a way Einstein could have only dreamed of, and with each detection, we're learning more about the cosmos. The universe is speaking through these ripples in space-time. The question is, are we ready to listen? Thank you for watching. If you liked the video, don't forget to give it a thumbs up and subscribe for more space insights.